about lecture first. So I'm going to say one last thing about Chapter 11. Section 5. So there was one example that we didn't go over, and it's actually in the book, but I thought I'd talk about it. I don't know what it specifically says for the problem, but it's talking about playing slot machines, which I don't know if anybody's ever played slot machines in here. You put in a coin, you pull a lever, these wheels spin, and they have different pictures on them. In this case, this might be the classic slot machine. You have pictures of cherries, oranges, plums, bells, melons, bars, and sevens. And so there are 20 pictures on each spinning wheel. And depending upon what results you win or you lose, and if you get certain combinations, then you win more money. So for example, one of the winning combinations is getting a cherry on the first reel. And then one is getting cherries on the first 2 reels. And then there's the possibility of getting 3 cherries. Now this first one was confusing to me because the way that, it's a counting problem. I mean, all probability problems are counting problems. So you have to figure out what the number of arrangements there are of these different types of pictures. And I forgot to turn it on there. Nobody told me that I didn't have my screen on, so let me turn the screen on. Yeah, I had a picture here, so let me show it to you. The whole fundamental counting principle says if you have a multi-step process, how many choices do you have in each step? And so once this comes up on the screen, and we'll explain how they come up with the numbers. No, it's coming. It's just warming up. I usually have it. That's one of the first things I do is turn that on, except today, because I'm thinking about the tests that I'm giving in the other class. So I am another good multitasker sometimes. So they call them reels. I think it's kind of like a movie reel. So these are the different images. And on the first reel, there are 2 cherries, 5 oranges, 5 plums, 2 bells, and so forth. Up to this total of 20 different pictures. And then you've got the arrangements in the second reel and the third reel. And so the question is, here are the different winning combinations. 1 cherry on the first reel. So you've got 2 out of the 20. Two. So this is just counting. How many choices do I have for cherries? There are 2 choices then, so you take 2 and you multiply by the number of ways they're not cherries. So there are 15 that are not cherries since there are 5 that are cherries. So 20 minus 5 is 15. Now, the thing that confuses me is they put 20 in the third place, which would indicate that it can be anything in the third reel. So you can have a cherry in the first and a cherry in the third. That doesn't give you anything. It's just having a cherry in the first, but not in the second. So I guess it depends on how you define the winning combination. Anyway, there are 50 ways to have 50 ways to leave your love. No, there's however many there are. 600 ways, 600 combinations out of the arrangements out of the 800 possibilities that have a cherry in the first row, don't have a cherry in the second row, but can have anything in the third row. And you get 800 by just multiplying the total number of images on each reel. 20 times 20 times 20 is 800. So the probability of winning with getting this particular win is 600 divided by 8,000. So that's the probability of winning. You put a coin in, and then you get multiple coins out depending upon whether you win or not. So it turns out if you get a cherry in the first reel and no cherry in the second reel and anything in the third reel, then you get 3 coins. And then you've got these other ones, 2 cherries on the first 2 reels and anything on the third reel. That wins you 5 coins with a lesser probability, 160 over 8,000. You've got 3 cherries, 3 oranges, 3 plums. Again, we have 2 times 5 times 4 gives you the total number of arrangements that have 3 cherries. And you can do that with all the other winning combinations apparently. 3 bells, 3 melons, which is the jackpot, and 3 bars, jackpot, 3 sevens is the jackpot. These have the lowest probability. And then they have the value, you get 500 coins back if you get 3 sevens, which is the least likely thing to happen. So it's 1 out of 8,000. This is 32 out of 8,000. So to find the expected value for this game is you take the probability of success, which are successes which are given here plus some more right here. So these are all the probabilities of success, and you multiply by the corresponding value, which is the number of coins. And if you add all those, the product of the probability times the value, and you add all those up, the answer is 6,318 out of 8,000. What that means is that if you played 8,000 times, you would get back 6,318 coins. So obviously you lose because they're trying to make money. Yeah, well, that's the thing is that's why people like slot machines, because they can, you win reasonably often, and so you have this false sense that you can win, you can beat the odds, and that's the whole thing. I mean, it's not stacked heavily in favor of the casino or whatever this has at slot machines, but it's definitely enough. So if you had this number too low, then people wouldn't play the game. So anyway, this would be your expected value if you charged, play 1 coin. So this is the gross winnings. The net winnings would be 1 minus that fraction, which is, so each time you play, you lose approximately 1.17 coins. So you play 10 times, you lose 1.7 coins. And so so if you ever play slot machines, you can think about this.
So our attendance question is about slot machines. So if you look up slot machines on Wikipedia, there is another name that slot machines were used, and they were called one something something. Okay, and it has to do with the fact that they originally had one lever that you pull down instead of pushing a button.
Okay. So we're going on to chapter 12. So chapter 12 is statistics. Obviously, we're not going to get as much detail as a statistics class, but we'll learn a few basic things. Some that you probably have already seen. And thank you. Thank you. Yeah, you can have this back. Yeah, you'll learn there's some things you should have already heard previously, and then there'll be some new things that you'll learn. And also, what I tend to do is use the spreadsheets to do most of the calculations, because a lot of the calculation statistics are are just, what's the word? Mundane, I guess would be the word, you know, just adding numbers together, dividing. It's fairly, the math is fairly simple. And it's fairly, what's another word? Formulaic. Is that a really good word? Meaning that formulaic. What does formulaic mean? Does anybody know? Yeah, you just plug stuff into a formula and you get the answer. So it's not like you have to think about which fundamental, is this a permutation or combination? You know, it's just doing the math. And you might as well have the computer do the math for you as long as you understand basically what's going on. We don't need to have overkill. So what we do is we use Google spreadsheets just because I think most of it well, let me ask you this question. If I said to do the problem using Excel, how many people do not have access to Excel? Yeah, that's why I have Office 365, which I have to learn how. I mean, I use an older version just because it's on my computer. But we could use Excel. I'll have to think about that since everybody probably has three. I'll ask the other class too. It's probably more useful to learn how to use Excel, even though if you learn to use Google Docs, a spreadsheet, it's, you know, you do one, you know, there's not a huge amount of difference between the actual mechanics. So anyway, so we'll introduce the concepts, and ultimately the grade for this chapter is a project. So it's a spreadsheet project, and I actually give you a video explaining how to do it. So everybody can do it as long as they take the time, and it doesn't take, you know, exorbitant amounts of time. So it's an opportunity to get 100 if you're willing to put in a reasonable amount of effort. Okay, so these are the topics. You don't need to write these down because we'll come to them. Just kind of give you an idea where we're going. So first is the visual display of data. We've done graphing before in the first semester. This is just a specific kind of graph called a histogram. It's a way of presenting data and being able to look at where the central tendency is, which we're going to talk about how to do that numerically. Looking at dispersion, you can do that graphically as well. So we're going to, in the second section, we'll talk about mean, median, and mode, and we'll talk about dispersion, which is standard deviation, and range. Again, those I'm sure you've had mean, median, and mode. Standard deviation, maybe. Position, it's called a z-score. Has any people have heard of z-scores? Okay, so that's your position relative to the mean. And then the last section is talking about a specific kind of distribution, which is a normal distribution. So what you can do is you can take a bunch of data, and if it looks normal by looking at the visual display of data and calculating the mean and the standard deviation, then you can use that information. Assuming it's a normal population has a normal distribution, then you can make some estimates of stuff. And in the whole concept, talking about statistics, there's two important terms: population and sample. And what population represents is basically all the items of what we're studying. So if we're talking about looking at grade point average of Dabney and Eskill Lancaster Community College students, you know, the population would be everybody who's here. A sample would be just a random smaller grouping of that larger group. So the sample is always smaller, and a lot of times you'll do statistics on the sample and then infer what the statistics are associated with the population. Typically, it involves randomly selecting your samples. You know, you're not going to take everybody in calculus and say that's representative of the general population. It's not going to. They're going to take more math and science classes. But if you were to go to each class and pick one person and just say, you know, pick a name out of the hat, then that would be more representative of a random sample. And then, you know, how many people you include in that sample. If you don't have enough, then it may not be representative of the population, but, you know, you're always trying to I shouldn't say you're always trying to do as little as possible. It is human nature, but you know, you want to do as little sampling as possible just to save time and money. So there's a trade-off between how many people we ask or how many experiments we run, and to get the best data, but to spend the least amount of resources on that. So that's the difference. Sample and population. Okay. And there are two kinds of statistics. We're only going to look at the first type of statistics, which is collecting, organizing, summarizing, and presenting data. So that's the easy part. If you take statistics 157, you would spend a lot of time on descriptive statistics, but you would spend some time on inferential statistics. So what that is doing is it's taking the data that you've collected here and then saying, is there a difference in the population, the results for the population that you're studying? So, you know, any scientific study, say it's looking at genetics or it's looking at medicine, disease, education versus income, all those kinds of things, you're trying to draw some kind of conclusion. And so there's two things that you do. Is at first, is my sample big enough, and is my selection random enough so that the sample is good? And then once I've tested the data, are the differences between the two samples significant enough that you can say there really is a difference? Because, you know, just because two things are not exactly equal to each other doesn't mean that they're different. You know, there's some probability that they may be the same based on the random selection, how you select your samples, how big the sample set is, that kind of thing. So that's a little more deep, takes a little more thinking to do inferential statistics. You know, they're changing the math sequence, not next year, but the year after that. Mr. Watkins is going to do kind of a pilot, and the way they're going to do it is the second semester is going to be entirely descriptive statistics. So instead of doing what we're doing, which is probability statistics, finance, something else, they're going to spend a lot on just descriptive statistics. If you want to get the inferential stuff, you'll have to take another statistics class, which will be a little bit more advanced than the current statistics class, but not. Okay, thank you. Anyway, you don't have to worry about that because you'll be done, hopefully.
So even though this is a short video, I've decided to put a second question in. So I want you to tell me what your favorite food is.
Okay, so when it comes to graphical display of data, or just display of data, we're going to use two things. One's called a frequency distribution, and one is called a histogram. The frequency distribution is just the tabular form of the data that represents the histogram. Because what you normally get is you get a big pile of data, and you know, say numbers. What's the average SAT score of some school? You get all this pile of SATs, so you get 300 SAT scores. So then what do you do with the data? You know, you don't just random list of 300 numbers and people look at it and go, yeah, okay, so what does that mean? So it's just a way of consolidating the data and then presenting it in a way that it gives you the most information in the least amount of space. So frequency distributions and histograms are the typical means of doing that. When I worked at Westvaco, I did a lot of experiments, and histograms were the main way that I would use to present the data. Usually what happened there was you'd be trying to improve or change the paper that they make their properties, so they would test the paper for various properties, like how what the strength is, if you pull on the paper like this, or if you bend the paper, how stiff it is, how white it is, how bright what color looks white, but it's really a shade of white, different shades of white. Anyway, there's all kinds of paper properties, and then you would have the laboratory test the paper before the change, and you test it after the change, and then you would look to see whether there was any change or not. So histograms were the way that I would do it. Most people would do it. There's another way called box plots, but I tended to use histograms as a way of doing that. So it's very useful. It's not just something. It's not just a math interest thing. It's used quite a bit. Okay, we're going to skip that. Frequency polygons. So here are the guidelines, and they're in your book. So you just need to know how to follow the rules. This is both for choosing the classes for a grouped frequency distribution. So what we do is it's kind of like you have, we always talked about it, it's like you have one of those old mailboxes like this, and it has, well, actually it's the mailboxes in our office here. You've got slots, and then you have names. And so when you're going through the mail, you go, okay, that's for Steve, that's for Ralph, that's for, Tom DeLay or whatever. You stick them in there, and you get piles of mail like that, and some people have more mail than others. Okay, so it's the same kind of idea, but you do that with data. You want to group the data into classes. In a mailbox, you're sorting them according to the person's name. What you would do in terms of data, which are numbers, is you specify a width, number range that you're going to put numbers in, classify them, and then you're going to, so you need to know the width. You also need to make sure that every piece of data fits into one of those little slots. So instead of mail, if I said from 100 to 104, I'm going to put those in that slot, and 105 to 109, I'm going to stick in that slot, and 110 to 114 in that third slot, and so forth, like this. That's why they call them classes here, but some people call them bins. So those are the bins. You'll put it in there. Oh, I got 118. Let me stick it in there. Now we don't actually do it this way. What we do is we might, well, let me do it on, I can't do it. Let me do it on the sheet here. So let me just go through these. So make sure each data item fits into one and only one class or bin. Try to make all classes the same width. Make sure the classes do not overlap, meaning that you can't put the thing in either one or the other. It has to go in one slot, or it can't go in two slots. And typically, you make it so that it has 5 to 12 classes. So if you have too few, then you don't have enough information. It doesn't tell you enough information. But if you do over 12, then you have too many classes, and it's hard to look at. It obscures the tendencies of the data. So the way we're going to explain this is we're just going to set up an example, and we're about ready to take the test. So I'm just going to explain what we're going to do next time. I've got a list here of data. So there's a whole bunch of numbers. And what we're going to do is we're going to take this data, and we're going to put it into these classes or bins, and we're going to count how many numbers are in each bin. And that's the information that you put into your frequency distribution. You don't put the actual numbers, but you count how many numbers are within a certain range, different ranges, and then you plot that data. Okay, so we'll stop there for today. And